Hey, everybody. For this series, I'm going to talk about thermal analysis. And this one is going to be about the heat transfer. As the fact that that there are three main types of heat transfer. The first one we're talking about is conduction. Uh, that's the transfer heat from higher temperature to a lower one. Um, that's the media seem to be solid. And the second one is the convection. For example, you turn on the fan and you feel more comfortable. It's cooling you down, and that's because the air transfer heat or uh, higher temperature, from your body, out to somewhere else. And the meteors that transfer heat that seem to be a fluid. In this case, is air. And the last one is radiation. For example, you sitting down under the tree with the shadow, but you still feel hot. That's because the radiation, that's the actually need no media at all. You can think about the sun um, to the earth, and the sunlight can radiate from the sun to the earth because there you have to go through space. There's no media at all. Okay. Well, take a look at the failure rate represented by lambda and T. The T is the gaseous. That's the temperature dependent. And also they have a terminology, thermal acceleration, represented by A equal to lambda T over lambda T0, where T0 can be room temperature. In this case, there you can put 25 degrees as reference. So for a failure rate, lambda, for higher one, that also show you thermal, show you higher thermal acceleration. And from chapter one, you know that the failure rate, that the junction temperature dependent, equal to A plus B exponential negative C multiplied by 1 over Tj plus 273 minus the 100, uh, 1 over 298, which is the 298 minus 273. That's the if you were 25 degrees Celsius. And also Tj plus 273, that's actually if you were the unit of Kelvin, absolute temperature, right? And also we also have a relation between the MTBF or mean time between failure. That's the equal to reciprocal of failure rate, lambda t or 1 over lambda t. If that's the MTBF. Now you also have you can set up equation n0 equal to nf t plus nst, where subscript f represents pair and s the represents survive, or your confidence still working, still good. And n0 is the number of components that you start in the system. And you also be able to calculate for failure rate. Uh, that's the time dependent equal to nft over n0t, where nf is the number of failure and n0 the number of components start in the system, and the t is in the unit of hour. And for this equation, for the failure rate, this means when you find components failed, you not replace uh, with the good one. But in the case that if you're running the system and you write some components that's work or fail, um, you need to apply this equation. In case that you replace the good one with the fail one. For example, for 2 hours, you find uh, one component fail, you put like two here, and you replace with the good one. And you keep working, and you find another one. Uh, for example, 4 hours later, you were replaced the second failed component with the good one. So you can apply this equation for the failure rate equal to NF over T1 plus T2 plus 2 N0 minus NF and multiply by T. Now let's take a look at the component reliability uh, in the term of probability. PST, that's survival probability. That's mean the chance that your component is still working. It's going to be NST over N0 according to equation 8.5 in my book, and also PF equal to NF over N0 according to equation 8.6 in my book. From this equation, N0 equal to NF plus NF, you divided both equation on the left and the right by N0. That's give you 1 equal to PS plus PF. Of course, survival probability plus the failure probability just give you 1. Corresponds to equation 8.7. And you also be able to derive for PST in the term of exponential PST in the term of failure rate. Let's give you a PST equal to exponential to the power of negative integration of lambda t dt. And for special case, the constant failure rate, lambda t equal to lambda 0, you simply just simply give you a PST equal to exponential to the power of negative lambda 0 t corresponds to equation 8.5 in the book. Now let's talk about our system reliability in the case that your system has so many components. We will talk about series arrangement and also parallel arrangement. And you know that um, for parallel arrangement in practical or in everyday life, if in parallel arrangement that gives you higher survival probability. For example, when you connect light bulb for New Year celebration or Christmas, you know that you need to connect light bulb in parallel, not in a series way, because if one light bulb blew up in a parallel, the rest still working. But for series, the rest uh, not going to work. So that's in the term of probability. Now, for series arrangement, if you have the survival probability of each component, in this case, we have a component, 4 components in the system, PS1 to PS4. PS of the system is going to be PS1 multiplied by PS2, multiplied by PS3, and multiplied by PS4. Where is, the survival probability PS. And you can write the term of mass in the term of PS of the system equal to exponential negative. This is in general form. It's going to be a summation of I equal to 1 to n lambda I. Here you have a n components connected in series according to the equation 8.218. Let's take a look at example. For lambda 1 equal to lambda 2 equal to lambda 3 equal to lambda 4 equal to lambda 0. They are the same. If you want to look for lambda 0 to achieve PS of the system to be 90% of, still works, still good, your PS of the system is going to be exponential to the power negative 4 lambda 0 t. Or you're looking for PS of the system to be 90% or 0.9. You apply Ln, and then you work out. You have lambda 0 equal to negative Ln of 0.9 over 4. Or your lambda 0 equal to 0.02634. For your survival probability of each component going to be exponential negative of 0.02634 for lambda 0 failure rate. That's give you a 0.974. Now for parallel arrangement, you look at the failure rate. So the failure rate of the system is going to be PF1 multiplied by PF2 multiplied by PF3, because the system has three components. That corresponds to your equation 8.19. And of course, you're looking for PS of the system. That's going to be your PF of the system going to be 1 minus PSS, PF in the term of our PS. And PF1, you can write the same. You can 1 minus PS1, and PF2, 1 minus PS2, and PS3, that's the 1 minus PS3. And you can expand the terms. That's give you your equation 8.20. And in the case of all components has the same survival probabilities equal to be 0. And they have in components in series and in rows in parallel. You simply can write down equation that going to be if you look at this one. That's going to be 1 minus PS of the system equal to 1 minus PS to the power n. That's the combination connected in series for n. And then for n rows in parallel according to equation 8.21b. Lower from the book, figure 8.68. For all components has the same survival probability, that's equal to 0.9. And you have all components in series. And you have 2 rows in parallel. So I put this one as the all components 1, 2, 3, 4. I put this one as PSS1. That's the connected in series, right? That's give you 0.9 to the power of 4. Same as the components 5, 6, 7, 8. Also 0.9 to the 4. And finally, they are connected in parallel. So your PS of the system going to be 1 minus PS of the system. That's your PFS equal to PF1 multiplied by PF2. And your PF1 equal to 1 minus PS1, right? So that's give you 1 minus 0.9 to the 4th. And the final give you 1 minus 0.9 to the 4th and to the 2nd. So your PS of your system here, that's going to be 1 minus this guy. 1 minus 0.9 to the fourth and to the second. And the PS of your system going to be a 0.882. For the figure 8.6b, you have one strap, or you can say that you have more components connected in parallel. This one is series parallel with one strap. So for component 1 and 2, they are in series. Let's give you the survival probability to be 0.9 to the second. And same for components 5, 6, 3, 4, even 8. And let's take a look at the left hand here. It's also connected in parallel, right? So for the system 1, you have PF1. It's going to be 1 minus PS1. And PF1 equal to PF12, right? In parallel with PF56. And the PF simply equal to 1 minus PS12. And you already have a PF12, right? 0.9 to the second. So that's why you have a 1 minus 0.9 to the second, and then to the second, because this term and this term are the same. And finally, you can find PS1 equal to 1 minus this guy. 1 minus 0.9 to the second, and to the second, that's gives you 0.964. That's equal to the survival probability of the system 2. And then they are connected in series. So you simply multiply PS1 by PS2. This gives you 0.964 to the second. You end up with 0.929. For figure 8.6c, same. PS1 equal to PS2 equal to PS8 equal to 0.9. This one is the series parallel with maximum cross strapping. Okay. That means they give you more parallel connection or arrangement. So you start a fan PF 15 going to be equal to 1 minus PS15. And for PF1, that's going to be 1 minus PS1. It's like SAM, right? F and S and F very close. You may confuse. So that's give you 1 minus 0.9. These are two rows. So let's go to power 2. Then you have PS15 going to be equal 1 minus this guy. 1 minus 0.9 to the second. That's give you 0.99. And they are equal, for components 1, 5, 2, 6, 3, 7, 4, 8. And they also connected in series. So your PS of the system going to be equal to PS of 1, 5, PS 3, 6, PS 3, 7, PS 4, 8, or 0.99 to the fourth. Let's give you a 0.61. So this is the summarization. I could like figure 8.6a, 8.6b, 8.6c. And this is your survival probability of your system. That's 0.882. It's getting higher and higher because you have more power connection. More strapping, better probability of system reliability or safe. More power arrangement give you better PSS or system uh, survival probability of your system. Okay, so we will continue with the thermal analysis series later on. Okay, bye.